Hello everyone and welcome to the next video session on the thermodynamics. So in today's class we are going to take a look into the enthalpy, the concept of enthalpy, very important. Okay, so what we have here for today is the enthalpy. So usually this particular enthalpy is denoted by H. Okay, so let's understand this enthalpy in detail. So here, let us consider that we are going to have one particular system. Let's consider this as a system. Okay, so in this system, let us say again that we are going to take a help of a piston. See, such kind of representations are quite important in order to visualize. Okay, make sure that you have a very good imagination power so that the things will be easier. Okay, so anyways, let's consider that this particular system is going to have certain amount of gas, let's say n number of moles of gas. Okay, so whenever we take any system, the system has certain amount of internal energy, correct? So this enthalpy is related with the internal energy with some more additions to it. So try to understand that enthalpy is actually nothing more than, it's nothing more than the heat contained. It is nothing more than the heat contained of a system at constant pressure. Okay, so this goes good when we are trying to define it, but when we try to understand it, it's way other way. Okay, it's going to be something like this. Enthalpy is nothing more than, when we take a system into consideration, it is sum of two things. That is, it is sum of the internal energy. Okay, so we already have this. As we have already studied about the internal energy, we know that every single system contains certain amount of internal energy. It is the sum of your electrical energy, chemical energy, mechanical energy, all the type of energies. Correct. So here, when we take a look into enthalpy, it is the sum of internal energy and the product of work done. The product of work, that is with respect to the pressure and change in volume. Okay, so this combination is going to give rise to the enthalpy. So we can also say it down as enthalpy H is equal to U plus pressure, volume, work. Okay, so we can say this. Now here, whatever we have enthalpy, when we calculate it, we need to end up giving its SI units, correct? So SI unit for enthalpy is going to be as, either you can give it as kilocalories or kilojoules. Extremely sorry, or kilojoules per mole. Okay, so either you can go as kilocalories per mole or you can go as kilojoules per mole. So that is going to be an SI unit of it. Now, let's try to understand this particular enthalpy into detail, into its depth. Okay, so as we have said that enthalpy is equal to U plus of PV. Okay, so that is going to be, enthalpy is equal to internal energy plus the product of pressure and volume. Let's understand with respect to a system. Okay, in order to understand the enthalpy into detail, let us say that we have a system, and in this particular system, let's say we have taken this n number of gas molecules, correct? Now let's say that to this system we are going to supply certain amount of heat energy. So let's give that heat energy that has been supplied is as Q. Thing is that we are neither going to increase or decrease any pressure. So therefore this entire process is going to occur at the constant pressure. So when I am subjecting heat at the constant pressure, please let me give this as Qp. So first thing that I need to note down here is the heat is supplied at the constant pressure, and so therefore let's give it as Qp. On the other hand, whatever this particular piston is there, now you are heating this, correct? So naturally the pressure inside this particular gases, inside this particular system is going to increase, and therefore it is going to exert pressure on this piston. As the pressure is exerted on the piston slightly moves upwards, so therefore work is done by the system here. Okay, so as the work is done by the system, second point that we need to note, work is done by the system. So as work is done by the system, we will take this particular work done as minus of W. Okay, so in this case, what is happening is there are going to be certain changes with respect to its volume, with respect to its internal energy. Now, here, let us say that this is the first condition as V1, and when this particular piston moves to the top end because of the internal pressure, let's say this is a position of V2, correct? So therefore, work done as what we have here is equal to P into delta V, correct? So this is nothing more than, as the work is done by the system, we will give it as minus of P into V2 minus V1. Is this correct? Now, at the same time, what is going to happen is there is going to be change in the internal energy. So, change in internal energy. Okay, now let's consider this. At the starting, whatever the internal energy that we had was, let's say, U1. And after this particular work is done, let's say U2 is the internal energy. So change in internal energy is nothing more than delta U. So that is U2 minus of U1. Is it correct? So now what shall we do is we are going to take this particular thing, that is your work done, and let's substitute this particular work done into the first law of thermodynamics. So therefore the first law of thermodynamics from the first law of thermodynamics. So from the first law of thermodynamics, what we have, delta U, change in internal energy, is equal to the heat supplied plus the work done. Is it correct? Now we shall substitute the work done. So therefore, substituting the work. Okay, so when we substitute the work, that is work is equal to minus of P into delta V, correct? As the work is done by the system, we have a negative sign. So therefore, we are going to have it as delta U is equal to Q minus of P into delta V. Okay, now let's observe these particular facts, that is a change in the internal energy and change in the volume. So when we substitute those particular terminologies, what we are going to have? Change in the internal energy, that is delta U, and change in the volume, that is going to be as a delta V, correct? That is V2 minus of V1. So taking those into consideration, U2 minus of U1 is equal to Q. Now please note that Q is going to be as Qp because the heat is being transferred. The heat is being transferred at the constant pressure. Correct. So Qp minus of P into the bracket of V2 minus of V1. So this can be written as U2 minus of U1 is equal to QP, okay, minus of PV2 plus of PV1, right? So now what shall we do is we will shift up the things. So as we shift up these things, what we are going to have here, let's shift V2 on the other hand, okay, and let's shift U1 on the right hand side. So therefore, we are going to have it as U2 plus PV2, okay, is equal to QP, okay, so plus U1 plus PV1. Now if we observe if we just recollect the enthalpy, so enthalpy is equal to the internal energy plus the product of pressure and volume, correct? So if we have that in our mind, if you see this combination, so this is the enthalpy term, so we will write it down as H2 is equal to QP. Okay, and this is again is equal to plus of H1, correct? So therefore, if we write it down as H2 minus of H1 is equal to QP, therefore, we are getting our first conclusion here, that is delta H is equal to QP. So remember this point first. Okay, so what is happening here is that it says when you supply heat at the constant pressure, it directly changes its enthalpy. That is, if we supply heat to the system at constant pressure, the enthalpy increases. If the system loses heat at the constant pressure, enthalpy of the system decreases. So in short, it is a measure. The heat supplied at a constant pressure is a measure of the enthalpy change. Okay, please note down this very important point. Okay, now on the other hand, let's proceed further. Now, if this entire process what we have done it at the constant pressure, correct? So if the change in volume itself is 0, that means it is a constant at a constant volume. Okay, if we are going to supply the things at a constant volume, then let's take change in enthalpy is equal to change in internal energy plus P of delta V, correct? But now here what we have, the delta V is equal to 0. As delta V is equal to 0, so we are going to have this entire term as 0, correct? So delta H is equal to delta U. But delta H is equal to Q. Remember this, whatever you supply the heat, it directly influences its enthalpy, correct? So let's substitute this. Okay, so substituting it by Q, but the Q is at constant volume. That is, if you supply the heat at the constant volume, then it changes directly its internal energy. So these are the 2 points which are the most important, and you need to remember these two. So therefore, one over here, and second one over here. So what we have here is that when you supply the heat at the constant volume, that time its internal energy changes. If you supply the heat at the constant pressure, its enthalpy changes, and this is how these two equations conclude. Okay, so in the next case, we are going to take a look into what exactly is the relationship between delta U and delta H. Okay, so coming towards the final point for this particular video, that is going to be the relationship between the delta H and the delta U, that is the change in enthalpy and the change in the internal energy. See, when we take a look into the solids or the liquids, in such kind of cases, very insignificant difference between the delta H and delta U. Almost both of them go in hand. Almost both of them are almost the same. But these things start changing as we approach the gaseous states. So in the gaseous states, there is going to be a particular relationship as how these two things are going to match each other. Okay, so let's observe. So in case of the gaseous states, let's say that we are going to have a system. And in this system, let us say that we are going to have a piston over here. Okay. So kindly note that the entire process as what we are going to deal here is going to be at the constant. It is going to take place at the constant temperature and constant pressure. Alright. So at this particular condition, let's say that we have two types of gaseous reactants inside. Now I'm saying over here reactants. That means these gases are going to react. Okay. So let's say that these are the two gases which are going to react. Now let's take this into consideration that VA, let's say VA is the volume of reactants. Okay, and let us say that Na is the number of moles of reactants. So let us say that this entire process is going to take place at the constant temperature and constant pressure. Correct. So as this reaction initiates, what is going to happen? Reactants are going to react and they are going to give us a product. Correct. So when a product is formed, let us say that these change to, let us say VB is going to be the volume of product, while let's say Na is going to be the number of moles of product. Quite simple as that, right? Now, this is before the reaction, this is after the reaction, correct? Now, if we are going to apply the particular ideal gas equation at this position, so what is going to happen? For the reactants, if we are going to apply it for the reactants, so we are going to have it as the reactants is going to be as PV is equal to nRT. But here we have taken as a volume of the reactants as VA. So I will write it down over here as VA. And Na is the number of moles, so let's write it as Na is the number of moles of those particular reactants. Now applying the same to the condition of our products over here. So when we have a product, let us give over here for the products. So for the products we have P into V is equal to nRT. But yes, again, what changes we are going to do is for the products, volume is VB and the number of moles is going to be NB. I'm extremely sorry, I should have written here as NB, right? Now, this is what condition is happening. PA is equal to, this is the condition what is happening. So can we write down this as P VB minus PVA is equal to NBRT minus NART. Alright. So from this condition, can we say that we can take the pressure constant over here. So VB minus of VA is equal to, let's take RT as common. So NB minus of NA Okay, so can we write down this as P into delta V, that is change in volume, is equal to RT into delta Ng. Okay, now Ng is nothing more than number of moles of product minus number of moles of the reactants. Okay, so therefore delta Ng is equal to the number of moles of product minus number of moles of reactants. Okay, so let's keep this. Now, let's rearrange for a moment. So therefore, it is going to be P delta V is equal to delta NGRT. Let's take this. Okay, let's have this and let's proceed further. So, when we have this an equation, we can again substitute the value of P delta V in our equation of the enthalpy. We can take this particular expression, that is P into delta V is equal to delta mgRT, and replace this, substituting this particular value. Substituting in the expression of enthalpy change. So when we have this enthalpy change, we can give it as delta H is equal to delta U plus of P delta V. Correct. So let us substitute this particular condition, that is P delta V, by this expression. So therefore we have our final expression as delta H is equal to delta U plus delta Ng RT. So this is our final expression, and this gives a relationship between the change in enthalpy, change in the internal energy with respect to the number of gaseous moles at a particular temperature. Okay, so I hope you have understood the importance of this. So you can actually measure the change in the enthalpy, or you can measure the change in the internal energy by the use of this expression. So therefore this expression holds a very important priority to us. Okay, so anyways, please do make a note of this particular expression, write down this particular derivation down step by step. Okay, so if there is any problem, you feel free to contact us. Do take care. We'll meet you in the next video. Stay safe.